In this video, we're going to discuss the Maclaurin series for the sine and cosine functions. Recall that the Maclaurin series for a function f of x is just the Taylor series for that function about x equals 0. It's given by the sum from n equals 0 to infinity of c sub n x to the n, where c sub n is the coefficient given by the formula the nth derivative of f evaluated at 0 divided by n factorial. To find the Maclaurin series for our functions, we're going to first find the first several derivatives of our function, evaluate those derivatives at 0, and divide by n factorial to find our coefficients c sub n. Once we have the first several coefficients, we'll look for a pattern to find a formula for c sub n in general. Our first task is to find the Maclaurin series for the function sine of x, and then find its interval of convergence. To find the Maclaurin series, we'll start by writing down several derivatives of our function f of x equals sine of x. We know that the first derivative of sine will be the cosine function, so f prime will be cosine of x. The second derivative will be the derivative of cosine, which will be negative sine of x. The third derivative will be the derivative of negative sine of x, which will be negative cosine x. The fourth derivative will be the derivative of negative cosine x, which will be positive sine x. And now notice that we're back at the beginning. We're back at our function f of x. And so continuing on in this taking derivatives, for example, to find the fifth derivative, we're going to keep repeating the same functions over and over. We have sine of x, then cosine of x, then negative sine of x, then negative cosine of x, and then we repeat those four functions. Sine of x, cosine of x. Of course, the sixth derivative will then be negative sine, and the seventh derivative will be negative cosine. We now evaluate each of these functions at x equal to 0, since we have a Maclaurin series, which is about x equals 0. F of 0 will be sine of 0, which is equal to 0. F prime of 0 will be the cosine of 0, which is positive 1. F double prime of 0 will be negative sine of 0, which will be 0. F triple prime of 0 will be negative cosine of 0, which will be negative 1. The fourth derivative at 0 will be 0. And the fifth derivative at 0 will be 1. Again, notice that we're going to have the four numbers 0, 1, 0, negative 1 repeat as we continue on taking derivatives and evaluating at 0. We now divide each of these values by the appropriate factorial to find our first several coefficients. C sub 0 will therefore be 0 over 0 factorial, which is equal to 0. C1 will equal 1 over 1 factorial, which is equal to 1. C2 will equal 0 over 2 factorial, and that will be 0. C3 will be negative 1 over 3 factorial, which we can write simply, which we can keep as negative 1 over 3 factorial. C4 will be 0 over 4 factorial, which will be 0. And C sub 5 will be 1 over 5 factorial, which we'll leave as 1 over 5 factorial. We now want to use these values for C0 through C5 to come up with a formula that gives us the values for all C sub n. Unlike in previous examples, this one's a little bit more complicated because we get different values depending on whether the subscript for a coefficient is even or odd. If we focus on those with even subscripts, C sub 0, C sub 2, and C sub 4 in the list that we have here, we notice that in all three of these cases, our coefficient is going to be 0. And this will continue on beyond C sub 5, because if we look at the even derivatives of our function, which would be the 0th derivative sine of x, the second derivative negative sine of x, the fourth derivative of sine of x, and the sixth derivative would be negative sine of x. All of these even derivatives end up being either plus or minus sine of x, and therefore when we evaluate them at 0, we'll end up with a 0 as our function value, and dividing 0 by any factorial will give us 0. And so we can conclude then that c sub 2n is always going to equal to 0. So here 2 times n is representing any even number, which can always be written in the form 2 times n. We now turn our attention to the odd terms. In this case, c sub 1, which we saw as 1 over 1 factorial, c sub 3 as negative 1 over 3 factorial, and c sub 5 as 1 over 5 factorial. And so here we have, we want a formula for 2n plus 1, c sub 2n plus 1. That's representing all of the odd coefficients, since 2n plus 1 is always an odd number. And here we see that our denominator is always going to be the subscript factorial. So here 2n plus 1 factorial. And our numerator is going to be an alternating positive and negative 1. For C1 and C5, it'll be positive 1, and for C3, it will be negative 1. And one way to do this would be to write it as negative 1 to the n in our numerator. Now that we have this formula, you can easily verify that it provides the correct values for C1, C3, and C5, and you could also check C7, C9, or C11, or as many of the terms as you'd like to confirm that this will then indeed give us all of the odd coefficients for this Maclaurin series. To actually find the Maclaurin series for sine of x, we're going to start with the series from n equals 0 to infinity of c sub n times x to the n, where c sub n are the coefficients that we just derived. We know that when n is even, c sub n is equal to 0, and so those terms will all be 0. And when n is odd, c sub n has the form of a negative 1 to a power over a certain factorial. So we're going to go term by term and just write out the first several terms of this series, starting with n equal to 0. Well, when n is 0, since that is even, we're going to have a coefficient of 0, and so we have 0 times a power of x. For the next term, when n is 1, we're going to have c sub 1, which is going to be 1 over 1 factorial, multiplied by x to the 1, or just x. When n is 2, that is an even number, and so we have a coefficient of 0, and therefore a term of 0. When n is 3, we're going to get negative 1 over 3 factorial as our coefficient, multiplied by x to the third power. When n is 4, we get a plus 0, since 4 is an even number, and c sub 4 would be 0. For n equal to 5, we're going to get positive 1 over 5 factorial times x to the 5th power. When n is equal to 6, we're going to again get plus 0, since 6 is an even number, and even coefficients are 0. And when we get to n equals 7, we'll get negative 1 over 7 factorial times x to the 7th. And we could continue on with as many terms as we want, but this is actually enough to see pretty much what is happening in our series. If we then rewrite this without all of the 0 terms, what we see is we have 1 over 1 factorial times x, which is just equal to x. We have plus negative 1 over 3 factorial, so we could write that as minus 1 over 3 factorial times x cubed. We can add to that 1 over 5 factorial, x to the 5th. And then subtract 1 over 7 factorial times x to the 7th. And then that pattern continues on indefinitely. We can then, if we want, rewrite these again further as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And now we can write this really clearly and really compactly as a series in sigma notation as the series from n equals 0 to infinity of negative 1 to the n. That will give us our alternating sign that starts with a positive, times x to the 2n plus 1. This will guarantee that the only exponents in our series are odd exponents, since we have x to the 1st, x cubed, x to the 5th, and so on. And the denominator is just the exponent factorial, and so in this case, 2n plus 1 quantity factorial. And so here is a compact form for the Maclaurin series for the function sine of x. Now that we have the Maclaurin series, we can use the ratio test to determine for which values of x this series converges, and therefore find the interval of convergence for this Maclaurin series. So to do this, we find the value of r, which is the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. In this case, a sub n plus 1 will equal negative 1 to the n plus 1. And then for our exponent, we need to replace n with n plus 1. And so we have 2 times n plus 1, quantity plus 1. And so this would be 2n plus 3 once we distribute the 2. And so our n plus first term here would involve the term x to the 2n plus 3. And this will be over 2n plus 3 factorial. We then multiply by the reciprocal of our nth term. So we're going to multiply by 2n plus 1 factorial over negative 1 to the n, x to the 2n plus 1. And this is our limit that we need to compute. We can simplify some of these terms. For example, x to the 2n plus 3 we can rewrite as x to the 2n plus 1 times x squared. And the 2n plus 3 factorial we can think of as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And therefore we have some cancellations with the 2n plus 1 factorials and the x to the 2n plus 1 terms. And so we're left with the limit as n goes to infinity of simply the x squared. We can leave that in absolute value if we like, but of course x squared will always be 0 or positive. It'll always be non-negative, and so no need for absolute values there. All over 2n plus 3 times 2n plus 2. And those values are also always positive, and so no need for the absolute values there. Notice the negative 1 to the various powers were canceled out with the absolute value. So now we have a fixed but unknown number, x squared, being divided by an expression that's going to get extremely large as n gets large, and therefore this limit is going to equal 0, and 0 is less than 1. And this is true for every value of x, and therefore our interval of convergence is the set of all real numbers, and in interval form that is negative infinity to infinity. And so this particular Maclaurin series converges for every real number x because the ratio of consecutive terms has a limit that is always equal to 1 for every x. If we now put together the various parts of the previous example, what we have actually shown is that for every real number x, the sine of x is equal to the series from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. In other words, that series is a power series representation for the sine function. We can use this power series representation in all of the various ways that we've used ones for the geometric series function, 1 over 1 minus x, and for the exponential function, e to the x. For example, suppose we wanted to find the exact sum of the series from n equals 0 to infinity of negative 1 to the n times pi to the 2n plus 1 all over 2n plus 1 factorial. We can compare this series with the Maclaurin series for the sine function that we just derived, which is the sum from n equal 1 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. If we compare our given series to the Maclaurin series for sine, we see that we could obtain the given series by setting x equal to pi in the Maclaurin series. Well, we know that the Maclaurin series is equal to sine of x for every possible value of x, and therefore the exact value of our sum is going to be the sine functions with x equal to pi. In other words, the sum is going to be exactly the sine of pi, which is equal to 0. If you'd like to try a similar example, you can pause the video and find the exact sum of the series from n equals 0 to infinity of -1 to the n plus 1 times pi to the 2n plus 1 over 3 to the 2n plus 1 times 2n plus 1 factorial. You can resume the video in a few seconds to see the full solution. We compare this given series with the Maclaurin series for the sine function, the sum n equals 0 to infinity of -1 to the n plus 1 times x to the 2n plus 1 all over 2n plus 1 factorial. We notice that if we let x equal pi over 3 in this Maclaurin function, then we'll obtain the given series, since we have a pi to the 2n plus 1 in the numerator and a 3 to the 2n plus 1 in the denominator of our given term. And therefore, the sum of our series is going to be sine of x with pi over 3 substituted in. So we have sine of pi over 3, which is the square root of 3 over 2. We now turn our attention from the sine function to the cosine function. Here we want to find the Maclaurin series for the function cosine x and also find its interval of convergence. One approach for doing this is to repeat the process that we followed for the sine function. Find the first several derivatives of the function, evaluate it at 0, divide by the appropriate factorial to find several coefficients, and then find a pattern in a formula for those coefficients. If we did this, we would get something very similar to what happened to the sine, with half of our coefficients being 0 and the other ones involving a positive or -1 over a certain factorial. However, we can avoid doing that in this case and can find this Maclaurin series with relative ease since we already know the Maclaurin series for sine of x. Here we're going to start with the Maclaurin series for sine of x, which we've seen earlier in this video to be n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Here we want the Maclaurin series for cosine of x, and we know that we can differentiate sine of x to get cosine of x. We also know that if we have a power series representation for some function, like we do here for sine of x, and we differentiate that power series representation, the resulting power series will be the power series representation for the derivative function, in this case cosine of x. So what we're going to do here is differentiate term by term the power series representation for sine of x to obtain the power series representation for cosine of x. We notice here that -1 to the n and the 2n plus 1 factorial are constants, and we're just multiplying the power function x to the 2n plus 1 by that constant. And so when we differentiate a constant multiple, we retain that constant multiple. And so here we just really need to differentiate x to the 2n plus 1, which we can use the power rule. We'll multiply, this will become the exponent 2n plus 1 times x to the 2n plus 1 minus 1, which is just x to the 2n. So we've brought down the power and then subtracted 1 from the exponent. Now we know that 2n plus 1 factorial can be thought of as 2n plus 1 times 2n factorial. And so here the 2n plus 1s will cancel. And what we're left with is the series from n equals 0 to infinity of -1 to the n, x to the 2n over 2n factorial. And this series here will be our Maclaurin series for the cosine function. In particular, notice that we did not have to compute a list of derivatives or evaluate them. We did not have to find the various coefficients and find a formula for those. We simply had to differentiate term by term the Maclaurin series for sine of x and obtained the Maclaurin series for cosine of x. To find the interval of convergence for this Maclaurin series, recall that for sine of x, the interval of convergence was negative infinity to infinity, since this power series converged for every real number x. And recall that when we use term-by-term differentiation, this does not change the interval of convergence. The radius of convergence in particular will always be the same when we differentiate. And since our radius of convergence for sine of x is infinite, the same will be true for the Maclaurin series for cosine of x. And so our interval of convergence here will also be negative infinity to positive infinity. Another option here to check for the interval of convergence is to simply apply the ratio test to this formula for the Maclaurin series for cosine of x. And if you do this, you'll see that you will get a limit of 0, which is less than 1 for every x, and therefore the interval of convergence is negative infinity to positive infinity. But here, because we're using the term-by-term differentiation technique to come up with this Maclaurin series, we can use facts about the term-by-term differentiation, in particular that it does not change the radius of convergence, in order to conclude right away that the interval of convergence is negative infinity to positive infinity. The previous example then can be formalized by stating that for every real number x, the cosine function, cosine of x, is going to equal the series from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial, and that this series will be a power series representation for the cosine function, cosine x.